going to get the exact same answer here between the two of them. So it doesn't matter which way. All right, so today what we're going to do is we're going to be looking at the derivative and the integration of square root of 25 minus x squared. We're going to do this on the domain of -5 to 5. So very first thing that we need to do if we're doing this is just find the derivative. And so, well, partially because it's calculus, and that's usually what we need to do. So first step is to do that. This part shouldn't be too difficult for any of you. But in order to find the derivative of this, the first thing we're going to do is just apply the chain rule. So you're going to kind of think of this as being 25 minus x squared to the power of 1/2. It'll make things a little bit easier. So the 1/2 is going to come out front, and then we're going to keep everything inside of that exactly the same, but drop our exponent up here by 1. And then we need to, like any chain rule, multiply by the derivative of the inside, which for this will be -2x. Now, when you get something like that, it's usually a good idea to simplify it, not use the negative exponents, whatnot. Simplify any integers if they do. So here, our 2 and our -2 will cancel. So on the top, the only thing that's going to be left is -x. And on the bottom, we're going to, because of course this, cross the line, flip the sign, we're going to put this down onto the bottom with a square root, which becomes 25 minus x squared. Okay, like I said, it shouldn't be too difficult for you. Just applying a chain rule to something. All right, so then from there, what we need to do is take a look at writing the equation of the tangent line to the graph when x is equal to -3. So in order to do this, there's two things we always need to do. I like to call it finding the pot, which is the point of tangency, and the SOT, which is the slope of tangency. So the pot is fairly easy. We're just going to plug in -3 into our original function, which was f of x. So we're going to find f of -3. Now for that, we need to use the original function, not the derivative. So that would be this guy right here, 25 minus x squared. So we're going to do the square root of 25 minus, instead of x, -3 squared, which is simply going to be the square root of 25 minus 9, which is really the square root of 16, which is really 4. So our pot is going to be -3 and 4. That's our point of tangency. Okay. Now our SOT is where we need to use the derivative that we just found, which was, of course, -x. So we're going to find the derivative at -3. So this becomes -3 when we plug in our x over the square root of 25 minus -3 squared. And again, I'm just using this derivative that we just calculated and plugging in -3. Okay, as I simplify that, the top is going to become +3. The bottom we can see is going to do the exact same thing here, right? 25 minus -3 squared is going to simplify all the way to 4. Okay, and so that will give us our slope. So now we have our pot and our SOT, and we can go ahead and write our actual equation. And so we're going to write y minus 4 equals the slope times x minus -3, which of course becomes +3. In doing this, I mean, you can always move the 4 over. It's not always strictly necessary, but if you prefer seeing it that way, then of course we can write it as y equals 3/4 x plus 3 plus 4. And if you really want to simplify everything out, you could multiply this in. To be honest, I don't know how often you're going to see it that way in your classes, but just in case, we'll go ahead and do that. So we're going to get 3x over 4 plus 9 over 4. We're going to have to convert that 4 to also be over 4, so 16 over 4. And then we can combine those and get our 3x over 4 plus 25 over 4. Now, the truth is, you're probably not going to see it written that way that often. Most of the time in calculus, we're totally fine with leaving it either this way or this way. But if you do want to try and get it into that original y equals mx plus b, then you can go ahead and do so. All right, so the next thing we're going to do here is we're going to look at continuity, because in calculus this becomes really important, because if we don't have something that's continuous, then we can't take derivatives. of them. We can't integrate them. And so it becomes really important for us to understand whether or not something is continuous. And so we're going to go back a little bit to some limits in order to do this. The reason for that is because we're going to use the definition of continuity, which of course requires us to understand that the limit from the left side and the right side of this piecewise function have to be equal. So the first thing we have to do is actually define that x of -3 exists in g of x. And so if we look at it, we want to make sure that g of -3 exists, which basically means we just need to make sure that somewhere on here it could be equal to -3, and it can. It's going to be our original function, and we already found that. We know that this is equal to 4. We did that in our first step. Our second step when we found the pot, right? So we know that it exists. The next thing we need to do is make sure that the left side is equal to the right side of these limits, okay? So that means that we need to work out what they both are. So if we think about it as taking the limit as x approaches -3 from the right side, so from the positive side where it is bigger than that, of g of x, we need to look up here. Is that going to be this top side function f of x, or is it going to be our new function here, x plus 7? Well, if it has to be bigger than -3, that's going to put it on this bottom function. And so that's simply going to be -3 plus 7, which is 4. And then we want to make sure that the other side is, of course, we've already done that, but we'll show it anyway. The limit as x approaches -3 from the negative side is actually of g of x is actually really just going to be equal to the limit as x approaches -3 from the negative side of f of x. And so really what that ends up becoming is, once again, just like we did before, -3 over, sorry, I'm putting that into the derivative, aren't I? That's not what we want to do. Well, let me erase it either. All right, let me grab. There we go. Now it'll let me grab the eraser. So we don't want that in there. We need to use the original function, and the original function was simply the square root of 25 minus x, so -3 squared. And this becomes the square root of 25 minus 9, which is the square root of 16. Like I said, we have done this before. I'm just showing it again to be thorough for us. And so it's, of course, 4. At that point, we can see that the left side and right side are both 4, and they exist at 4. So therefore, the whole thing is going to be continuous. Okay? It exists. The limit of the left side is equal to the limit of the right side. Therefore, all of that together means it is continuous at x equals -3. All right, so now we get into the part that's a little bit trickier, where we're going to be using some integration. And if you look at this, you can probably tell right away that this is not going to be an integration that is as straightforward, and so we're going to need to use a U-Substitution. That should always be kind of your first check, see if you can do it, especially if you're seeing something that's got, something that kind of looks like a product rule, so two things multiplied together, okay? So what you're going to do is we're going to say let u equal, and we're going to make it equal to everything that's underneath this root here. So we're going to make u equal to 25 minus x squared, okay? If we do that, of course, anytime we do u, we need to also figure out what du is, because we can't leave the u there and then have dx. We need to have everything be talking in the same variable. And so in this case, our du, if we look at this, is going to be -2x dx, okay? Now the good thing is that helps us out because that helps us find that x, it gives us our dx. The only problem is we've got this -2. So what we really need to do is take this entire thing and multiply it by -2 over -2, which is really just a fancy form of 1. So we can take this derivative, multiply it by that, and then what we're going to do is we're going to kind of manipulate it. The way I like to often say it is that we cannot be numbered gods, but we can be demigods. So we cannot create or destroy any new numbers, but what we can do is we can manipulate the heck out of them. So by multiplying by this really fancy form of 1, what we're going to do is we're going to put some of that inside of this integration so that we can get this du to look, or so that we can kind of manipulate it to look like -2x dx. So that means that this negative 2 on top needs to come inside. So on the outside, we're going to have negative 1/2. And then this negative 2 comes in, negative 2x, square root of 25 minus x squared dx. At that point, now you can see where our u and our du are. So we're going to end up with negative 1/2, sorry, multiplied by the integral from 0 to 5 of, and right here you can see these combined give us our du, and then this part here gives us our u. So we now just have the square root of u du. This, of course, is much easier for us to integrate, and so we're going to get that there's the negative 1/2 there out front, and the integration of this is simply going to be u to the 3/2 divided by 3/2 plus c. And then, of course, we would end up evaluating this, not actually from 0 to 5. We should manipulate these. I'm going to leave it the first time because I'm going to substitute back in. The other option is to change our bounds. I will do it that way afterwards if you'd like to see it done that way. So from here, we just need to simplify out what these fractions are here. So anytime we divide fractions, hopefully we all know or remember now that we're really just multiplying by the reciprocals of those things. And we can see that those negative 2's are going to cancel. U to the 3/2 plus c. All right. Now we're going to evaluate that from 0 to 5. But before we do that, we need to actually substitute back in because we weren't doing u, we were doing x. So we're going to have negative 1/3. U was actually 25 minus x squared. And that is to the power of 3/2. Now, hopefully by this point you remember as well that if we're evaluating a defined integral, the c doesn't really matter because we're going to end up adding and subtracting that same constant value. So at this point we can kind of choose to ignore it and simply plug in our evaluation. So we're going to get negative 1/3 multiplied by 25 minus 5 squared, all to the power of 3/2. Then we're going to, from there, subtract negative 1/3 of 25 minus 0 squared, all to the power of 3/2. Well, this one here, hopefully you can see that we're going to end up with 25 minus 25. So realistically, this whole thing here just goes to 0. So we're going to get 0 plus, because negative times a negative, 1/3, the 0 squared effectively disappears. So we just have 25 to the 3/2, which then means that I've got 1/3 times 25 to the 3/2, which is really 125 over 3. Okay? So that would be our final answer. Now, as I did say, if you'd like to do it a different way, rather than substituting back in, we can also just simply change our bounds. So what I'm going to do is go back and show you that. We'll do it in another color, maybe not red. Let's do blue. And what we're going to do now, oops, is come back up to here, this step here. Yes, right here. Technically, we could or maybe even should do this a little bit earlier, but right here is where we've at least simplified things so that we knew that we were doing negative 1/3 u to the 3/2 plus c, evaluated from 0 to 5, but we weren't really evaluating from 0 to 5 if we're doing u. So what we want to do is change those boundaries, okay? So we need to change our two boundaries, and so we're going to change the one at 5, which means that in reality u is actually going to be equal to 25 minus 5 squared, because I'm simply plugging 5 in for x. Remember, our original substitution was u is equal to 25 minus x squared. So I'm putting in 5, okay? That means that here we're going to get 0. So this boundary up here is actually going to become 0. Now our other boundary was at 0, which means that we get u is equal to 25 minus 0 squared, which simply means that it's 25. So we're going to change that 0 to 25. And this is what we would be evaluating between if we don't re-substitute back in and make it x's. Okay, so from there, like I said, just like before we did, we're going to plug in our 0 and then our 25. So I get negative 1/3, 0 to the 3 halves, minus negative 1/3, 25 to the 3 halves. Hopefully at this point, again, you can see that 0 times and to an exponent is simply going to be 0. The double negative will become positive, 1/3 times 25 to the 3 halves. And you should see that once again, that's the exact same thing that we had before. So simply 125 over 3. So whether you want to do it by changing your boundaries or whether you want to do it by resubstituting in what U originally was, you can see that we're going to get the exact same answer here between the two of them. So it doesn't matter which way. All right, guys, I hope you found that helpful, and check out more of our videos.